always. Oh, look it. You gotta wake up. No argument.
It's time to stick your finger in your third eye. Please to wake himself up.
You even have to get your dog awake. It's just time.
All right, so welcome back. Today we're going to continue on searching and sorting. But before we do, I would like to go ahead and do a little bit of a recap to see where we were doing late last week. Basically, we introduced the idea of abstract programming, generic programming, so that if you were going to say write one linear search algorithm or one linear search implementation, you only had to do it once. And that problem was solved for the rest of your life. You still needed a component that took two elements and ordered them. That said, yes, this is what here's the key element that you're giving to linear search, and here's the element that you're looking at in the array right now. They match or they don't match. Or more generally, like when we were looking at Quicksort, the Quicksort implementation, then it was the Quicksort knows how to order things, right? It knows how to sort, but it doesn't know how to order. So given these two elements, here's A and B, does it go like this? Or they're out of order, they need to be swapped, or they're equal, so leave them alone, right? And here's the visualization of that idea. Again, this is just a generic sorting algorithm. It doesn't know if this is integers, doubles, strings, whatever, right? You give it an array of stuff, right? It's generic, right? And it outputs a sorted array. Well, how does it do it? Anytime that it's given two elements A and B, it hands that off to this other comparator that is given as part of the input. And it returns, the contract here is that it returns something negative if A comes before B. It returns 0 if they're equal. And it returns something positive if they're out of order, if A comes after B or B comes before A, right? That's the basic idea of a comparator, okay? Now what I wanted to do is, last time we of course had some practice with this. We looked at how to write a comparator. A comparator returns an integer value, and it takes two const void star pointers. It doesn't take two integers, it doesn't take two doubles, it doesn't take two chars, right? It takes two generic void pointers, which can point to anything in memory. The first thing that you need to do in a comparator is to convert those to the types that you do expect. This is a comparator for integers. And so we will have to convert them over to integers in order to say that this one comes before this one or whatever, using this less than operator or greater than operator, or the only other possibility is that they're equal, and so we return 0. Right? Then, and of course, we can define other comparators that have the reverse order, or that order things differently, and that's what we're going to start out with today. But otherwise, once you have your comparator, then you don't have to write any sorting algorithms. You don't have to write any searching algorithms. You use what's built into the standard library. In this case, Quicksort. It takes the array that you want to sort, the number of elements in that array, in this case 9, the number of bytes in that each element in the array takes. Why? Because if it were integers, like it is right here, they're 4 bytes. And so Quicksort knows that it needs to take these 4 bytes and these 4 bytes and swap those 4 bytes. If it were doubles, it would need to know that there are these 8 bytes over here and these 8 bytes over here, and they have to swap those 8 bytes. If it's something else completely, then it has to know how many bytes are over here and how many bytes are over here in order to swap those. But otherwise, all you do to give it the comparator is give the comparator's name. Note, this is the function name that we defined up here. In this case, cmp int desc. We do not use the parentheses because that would be calling the function. We're passing this function, which is a function pointer, and that's something that we're going to get to by the end of the day here. But to recap, I wanted to get a little bit more practice, especially for your lab tomorrow. And so what I've done is I've set up a structure. How do we do this with structures? Doing it with integers is pretty simple. How do we do it with structures? So I've set up a pretty simple structure here with a variety of data types. An integer to represent the count number, 2 strings to represent the owner's first name and their last name, and a balance, which is a double, right? So that we've got all 3 basic types here to play around with. I've also got a function here to print them out. All it does is print them out in a nicely formatted manner. You can see that here. I'm going to go ahead and GCC everything together so that I don't have to do it multiple times. That's just a shortcut. There we go. So I've got these bank accounts set up in this demo over here. There's me, and I only have $42.42. But Joe Smith has $1,000. Zelda Smith has $300,000, etc. Alan Turing has $1,000 and a few pennies more than Joe Smith. And Grace Hopper here has over $100,000 in her bank account, right? So there's our accounts being printed out here. What I want to do is I want to sort these accounts by some measure. So our first step will be to define a comparator, okay? Now, a comparator has to have that signature. It has to return an integer. You can give it whatever name you want. I'll go with CMP for now, right? And then what does it take? Does it take two bank accounts? Does it take bank account A and bank account B? Right? That's not a comparator, right? I mean, that's some function. It's just like the strcmp takes two const char stars. That's technically not a comparator. Right? It's something that compares strings, but it is not a comparator. To be a comparator, you have to have that signature. Where was it? Down here, somewhere in the notes here. Oh well. In any case, it has to have this signature right here, right? It has to take two const void star pointers. Okay. So this is not a comparator. How do I make this a comparator? Const void star A and const void star B. All right. Now, what should I'm going to make this a comparator for bank accounts. So we've got several pieces of data here. How do you want to sort them? We could sort them by, balance, highest first or lowest first, ascending order, descending order. Say again? Ascending, so lowest first, highest down here. Okay, let's go ahead and go with that. Now, if that's my order, then I should label the comparator. I don't want to just say CMP. CMP what, right? It's for bank accounts. Bank account. Account by balance. And we'll just make this the default ascending. So if it were descending, then I would go desk or something like that. You could go ascending if you really wanted to, but you don't have to label everything, right? It's already pretty long as it is. So let's go ahead and take that and let's go ahead and implement this, all right? Bank accounts by balance ascending, right? So my first step is, of course, to force these two things, A and B. They're just memory locations. A is pointing over here, B is pointing over here. I have to know something about them now, right? Quicksort doesn't need to know anything about them, but I need to know, the comparator here, does have to know that they are bank accounts. So it has to force them to become bank accounts. Step one, cast them as bank accounts. Right. So const bank account star X, right? Or account 1 or account A1 or something like that if you really wanted to, is equal to const bank account star, and I will cast A first. Right? And then the same thing for, B. There we go. Okay. And by the way, you can't call them 1 and 2. Why? Those are never valid variable names. You can't begin a variable name with a number in most programming languages, right? Because compiler writers are lazy, and that's difficult to deal with. Is this a literal or is this a variable name? Well, if it starts with a number, then it's it's a literal, right? That's an easy rule to implement. And so compiler writers put that into their, or language designers put that into their languages usually, okay? All right, so now that I've got bank accounts, I can actually make a comparison. I'll make a comparison based on the balance here, all right? So if X's balance, X dot balance, is less than Y's balance, you said that you wanted to do this in ascending order. So if if X is less, then it comes first. All right, so they are in order in this case. So return -1. Now, is this correct? Is this a dot operator here? What is X? Is it just a regular old structure, or is it a structure pointer? Structure pointer. So is this going to work? Nope. I want the arrow operator here. Now, of course, I could have dereferenced it if I really wanted to, and then made it into a regular structure, And then I could have used the dot operator here. Well, that's extra steps. All right, else if X has a larger bank account balance, then they are out of order, right? Because X here needs to come, you said ascending order larger, so it needs to come last, right? So I need to return 1. Else, the only other possibility is that they have an equal amount, and so I'll return 0. I could have checked for 0 up here, or as the second case. The thing is, floating point numbers, something could be 0 and something could be negative 0. Something could be 0 and something could be very, very, very close to 0. And maybe you would consider those equal, right? So there are issues with floating point numbers. If you check for inequalities first, and eliminate the possibility that they're equal and that one's last, you kind of take care of a lot of those issues. All right, so that's a good comparator there. Let's go ahead and compile. Oops. Let's go ahead and compile this and see that it works. Okay. Oh, now I need to use it actually, right? So I've got my bank accounts here. I just set this up. This is a way of quickly initializing an array of a static array of structures for testing purposes. Feel free to do this, right? Especially this week with I think your airports or whatever, right? So I've got my bank account. These are the account numbers over here. These are the balances, first name and last name, obviously. And so let's go ahead and we print the accounts in the order that we've set them up. Now let's go ahead and Q-sort them, Quicksort them. Now remember, what are the arguments to Quicksort? That's the array that you want to sort, the number of elements in that array. Then, let's go ahead and go up here. There we go. The number of elements in the array, the size, which is not the size of the array, it's the size in bytes of each element in the array. So how many bytes does each bank account take? Size of bank account. Yeah, I'm not going to go and do the math, right? That's the compiler's job. Let it do its work, right? I don't want to have to go in and say, oh, okay, well, you have 2 pointers, that's probably 8 bytes. Another integer, that's another 4 bytes, so a total of 16, 4, 20, and then another double, so 28. And then I could be wrong entirely because it could be padding it out with bytes under the hood. So no, let it do its job, okay? So the last thing that I give it is the comparator that you want to use. In this case, compare bank account balance by balance ascending, right? And when we compile this and run it, it worked, right? The unordered version was printed out up here. The ordered version by bank account in ascending order worked. What if we wanted to do this a little bit differently? Give me another ordering that might be valid or that might be important. Last name alphabetical, okay. Bank account by, I'll just call it name. Okay. And let's go over here. There we go. Now I'm going to go ahead and steal, cut and paste the casting. There we go. Okay. Now I want to compare by the last name. But you know what? We have 2 Smiths here. How do we break that tie? Which one would come here first, Joe or Zelda? Or which one should come first? Joe. Okay. So let's go ahead and do that comparison. What I'm going to do is I'm going to store that off. Int result. Now last names. Last names are strings. How do I compare strings? I got to write another comparator? No. I'll just go ahead and use the one that's built in. strcmp of X's last name versus Y's last name. Right? And I'm storing that result, that value off into result. So that Smith, well, those are equal, so it'll return 0. Burke, Smith, Burke comes first, so that'll return something negative. Smith, Turing, Turing comes first, so that would mean that they're out of order and it would return something positive. All right. Of course, I need to bring in the string library if I'm going to do this. Now, what do we do about ties? What if they have Smith Smith? To break that tie, I'll go off to the first name. So if they have the same last name, if the result is 0, then I need to break ties by looking at their first names. Result will end up being strcmp of X's first name and then Y's last name. Right. Now that begs the question, what if we've got 2 Zelda Smiths? Zelda Smith, Zelda Smith. Go to the middle name, maybe. Go to some unique identifier to absolutely break ties so that it's a total order. That sounds like a better idea. I don't have that in this case, though. So Zelda Smith, without any other information, it doesn't matter what their ordering is. You could have Zelda Smith A and Zelda Smith B, or Zelda Smith B and Zelda Smith A. It doesn't matter. But if you really wanted to break ties absolutely, then you would need to use a universally unique ID of some sort, right? A social security number, a tax ID, or an account number maybe, if that's guaranteed to be unique. Okay? Otherwise, in this case, I don't really care. Result. Now, let's go ahead and Quicksort again with this comparator instead of that comparator. All right? And we'll print them out one more time. Oops. Last name. Oh, I screwed up. Last name, last name, first name, first name. That would have been a weird ordering, right? I don't know what it would have looked like, but this is a small enough sample that it doesn't really matter. What? Oh, owner first. Okay, owner. You know what? Yeah, owner. Last name. There we go. And owner first name. There we go. All right. Let's run that again, and I'll expand it out here to see. There's the original ordering. There's the ordering in ascending order by balance. And there's the ordering with respect to names. Burke, Hopper, Smith, Smith, Turing. But then the Smiths, they are broken by their first name. Joe comes before Zelda. What if I wanted to do something weird and, I don't know, switch those around? Come on. Didn't want to go that high. Come on. Invisible. There we go. What if I switch these around? Y and X. What ordering would I get now? Now, I get Zelda coming before Joe, but the last names are still in order. Okay. That's what you asked for. That's what it gave you. Okay. Questions on this so far? Because that's how you use it for with comparators, with structures. You simply force it to become the structure, and then you do whatever you need to do for the business logic for ordering these things. Now for C, it's not going to matter all that much, but there are languages that require, or at least highly encourage you to have what's called a total ordering. Like I said, what if we've got 2 Joe Smiths here, right? If I've got Joe Smith A and Joe Smith B, if they're the same person, then yeah, of course, they're equal. But if they're 2 completely different Joe Smiths in this world, and there are plenty of them, in fact, I've had courses before where we've had people with the same first and last name, and it gets really, really confusing awarding grades like that. And so we have to go to NUIDs and stuff. And so you have had situations where people have the same first name, same last name. That if you just use those 2 criteria, you would have what's called a partial order. How do you order these 2 people with the same first name and last name? Either way is okay, right? That's a partial order. What a lot of programming languages require is that you have a total order. If you don't have a total order, then for all intents and purposes, these 2 elements will be the same, and it might throw one of them out, depending on the data structure that you're using. So it is good practice to have a total order and break ties arbitrarily with some unique identifier. Okay? That's not going to matter much for anything that we're doing here. So don't worry about it. All right, that's our demonstration. I'm going to make sure that you've got all of this in. Well, let's just go ahead and put it over there now. Let's see. We didn't write any. I guess we should have this over there. And finally the demo over here if you really want it. There. Okay. All the code has been copied over here so that you can check it out later if you want to. Okay. All right. Let's end that. There. So what I want to do is I want to take a little bit of a deeper look at this. Okay. So what I mean by that is what are these comparators? How are they actually used? These are called function pointers. How can we pass a function to another function so as a parameter so that that function can use or call the other function, the passed function? Right? That's basically what we did up here, right? This idea right here, that we were passing this function to the quicksort function as input. We weren't calling it, right? We weren't invoking it. Quicksort was invoking it because every time it had two elements, it passed those two elements off to the passed function so that it could do what it was, so that it could ask what the relative ordering of those two things are. Doing so is generally referred to as a callback. Right? A function passed to another function is the callback, and the function invoking it calls it back. Right? That's my best guess for why these things are called callbacks. I've never been able to find the etymology of why it's called a callback, but it's a callback basically, and it's unfortunately something that we're not going to get to this semester because of the updated schedule. But if you want to, you can check out Lab 14, which is optional. It happens in graphical user interfaces all the time. Graphical user interfaces, right? Where you define a button, for example. What function gets invoked when a user clicks the button? Right? Where what function gets invoked when the user clicks a button? So what happens when you create this button, you have to register what's called a callback. You say, all right, button, create you and also your green, and the letters that you print on that button are go, blah blah blah, and also you're on this part of the window application or whatever. And by the way, when you get clicked, in the event that you get clicked, call that function over there. How does it say call that function over there? It takes that function and gives it to that creational function. When that button is created, it gives it to that button so that that button doesn't call that function. It waits until somebody actually clicks the button, and then it calls that callback. That's why it's called calling it back, right? Another example, again, is the one that we've been using, is Quicksort, right? It needs a way to order elements. So you pass in a comparator as a function pointer, right? But how does this all work? A function is simply code that is stored in memory. Right? Well, what else is stored in memory? Integers are stored in memory. Doubles are stored in memory. What else? Everything. Everything is stored in memory somewhere, right? That's what a computer is. It stores things in memory. So a function is simply just code that is stored in memory. Well, that means it has some memory address, right? i.e., the function is stored at a particular memory address in the stack. Right? So you can create a pointer that points to the code of a function. This is known as a function pointer, right? And you can actually use these things yourself if you want to do meta program, or if you want to do generic programming yourself. So let's go ahead and look at a demonstration here. What I'm going to do is I'm going to make copy demo to .c to demo ptr.c, and let's open that up. I'm going to go ahead and get rid of all this stuff because I want to focus on the function pointers now. So let's look at, first of all, the syntax. Let's create a function pointer called ptr2func, right? That'll be the function pointer's name. That can point to any function that, 1, returns an integer, and 2, takes 3 inputs: an int, a double, and a char. Right. I've never, this is no function I've ever heard of, but I just want to demonstrate the syntax of using function pointers themselves. So here's the actual declaration: int ptr2func. Right. Right. There's the return type. It returns an integer. That's number 1, returns an integer. I put in parentheses here because of the order of operations, and I make sure that I put this star here to indicate that it's a pointer. That's just the name. If I didn't have this, what would that be? That's an integer pointer. It points to an integer. By putting these parentheses here, I'm saying that this is actually a function pointer, right? And I would put in the parameters right here. Right? Now, what's this pointing to right now? Well, what is any uninitialized pointer pointing to? If I just have a regular old integer pointer, int star array, right? What's that pointing to? Big question mark, right? It could be pointing to anything. So how do I set it equal to null so that I know that it's not pointing to anything explicitly? ptr2func is equal to null, right? So make the pointer point to null, right? Or null, there we go. It's just like any other pointer. You can make it point to whatever you want. I could make it point to a function like ptr2func. I could make this point to the square root function, doing something like that. That won't work, however. Let me go ahead and try to compile that. It's going to complain. In fact, it's an error because, well, fine, bring in the math library. Right. GCC it and bring in, link it in. And, okay, it's just a warning. Good. Why is this a warning? Assignment from incompatible pointer type. ptr2func and square root. Does square root return an integer? Nope. Square root of 2 is 1.41 blah, blah, blah. That's no integer, right? Not only that, but does the square root function take 3 arguments? No, it takes 1. And that argument is a double, right? So let's make it point to something else. In fact, to do that, we're going to have a different pointer here. Let's make a function pointer that can actually point to the square root function. Double ptr2sqrt, right? And double. Right? So same syntax. There's the return type. There's the name of my pointer, and there's the single parameter that the function would take. This can point to any function, just like we saw here, but of course it's not going to be valid. Just like a comparator, if you make a comparator for integers and then you try to use it to sort doubles, that's not going to work. Right? You're going to have some typecasting there that's not going to work, or it will work, but it just won't give you the results that you want. So now I'm going to make this point to the square root function. Right? There. I did not invoke it because the name of a function is its identifier, is its pointer. SQRT is a memory location, right? That's the convention. PTR2SQRT, that is also a memory location. So these two things are compatible. There are other ways to do this. For example, you can get the memory location, but these two things are basically the same thing. So why write more? Right? You can get the memory location of a function by its name, or you can just use the name directly, just like an array. If I have an array, int star ARR, the name of the array is its pointer. You don't have to go later on, you don't have to go ampersand ARR because it's already a pointer. SQRT is already a pointer. Pointer to SQRT is already a pointer. Once we have that, we can start playing with it. Int y is equal to sqrt of 2.0. Printf. This is a normal way of calling a function, right? Square root of 2 is %f and the line. And I'll print out y here. Oops. Not double. Now I want double. Sorry. Double. There we go. Ah. Fine. When did I lose the IO? Oh, I guess I replaced it with math. Okay. So what's the square root of 2? 1.41 blah, 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 whatever, right? That's the normal way of calling it. Here's another way that I can call it now that I've got a pointer. PTR 2 square root of 2.0. And I can store that value that is returned by that function pointer and print it out. Same result. So what's the point? Why did I do this? This was just to demonstrate syntax. You already have sqrt. Why do you need a pointer to it if you could just call sqrt? The reason you need a pointer to it is if you're going to hand it off to another function so that that function can call it. To see what I mean, let's write a function that invokes math. Double. Run math. Right? And here's my input, double x, and here's my function, double func, and it takes a double. What I just did is I created a function that takes a regular old double value, right? But also it takes a function pointer. That function pointer it can point to any function that returns a double and takes a double. And now I don't know what function that is. It could be the square root function, or it could be the sine function, or it could be the cosine function, or it could be any math function that takes a double and returns a double. Now let's go ahead and actually run the math. Double y is equal to func on y, x, right? And return y. Now let's see how we can run this down here. Y is equal to run math. I'm lazy. I don't want to run my own functions. I don't want to invoke my own functions. I'll let that function do it for me. 2.0, and I'll go ahead and run the square root function and print it out. Oops. Whoa. I don't know what I did there. Okay. Too quick on my quick keys. Sorry. And let's go ahead and run that. Right there. I'm letting the function do that work for me. The heavy lifting. Well, why would this work? Here's another example. Right? I'll let it run the sine function instead. Sine of 2, and does anybody know what the sine of 2 is? There we go, close to 1. Right? Or, give me another math function. Fabs. Right? And I'll make it -2. Fabs of -2 is... There. It's running all my functions for me. Awesome. What's a use case for this other than sorting? What I've typically assigned in the past is integration. So a numerical integration. You've got a Simpsons method or a trapezoid method or something like that. Well, if you were to write a trapezoid method for the sine function, or a trapezoid method for the x squared function, or a trapezoid method for another function, right? Or you can write one trapezoid method that takes a function, math function, that simply then that function calls that function to do the integration. We don't assume calculus in this class, so I don't do that. But that's another use case that I've frequently used. Of course, graphical user interface programming, and more relevant here is searching and sorting. So there's a demonstration of how to use these things. What I want to do now is go back to square one, and what I want to do is I want to rewrite the linear search algorithm that we started everything out with. So remember this linear search algorithm? Right? Search doubles, search integers, search strings, search airports, search transactions. I want to take care of this once and for all. I want to adapt this search algorithm so that it's no longer just for integers. It's for double. It can be for doubles. It can be for chars. It can be for airports, whatever. In this case, I'm going to make it so that it's okay, also okay for bank accounts. Right? So search. In fact, I'm going to just rename it linear search. Okay. We're going to play around with this with a couple of iterations. Right? Let's go ahead and start with a naive, straightforward iteration version of this, where we take airport. Airports. Here's the array. An array of airports. A const airport star key. All right, there we go. So we're taking an array of airports of size n and this key element here that we're searching for. Okay? And then we're going through, and instead of asking is it equal, we can search for, not airports. What am I trying to do? Bank accounts is what I wanted. Bank account. There we go. All right. I want to search for a bank account by ID, let's say. All right. So the ID here is, I'm searching for a particular bank account, say my bank account with ID 1234. Okay. I'll go ahead and go back over here and, no, I'm done with that. Let me go ahead and get rid of that. And, where happened to my linear search? Oh, I put it over here in the header file. I should be over here in the source file, sorry. There we go. So, what I'm going to do is I'm still going to pass in a bank account key. It's going to be called what's called a dummy key. Let me demonstrate that first, actually. And let me go ahead and get rid of all this now that we're done with it. What I'm going to do is I'm going to create a dummy bank account key. Bank account key. And it'll have the bank account number that I'm searching for, but the rest of it, I don't know what it is. That's why I'm searching for it. I don't know that it's owned by me. I don't know what the balance is, so we'll just say 0.0 because that's not important, right? This is called a dummy key because you've only filled it with the values that you're interested in. Now, what we're going to do is we're going to search through this account, this array of counts for anything that has the same account number. Okay? So let's go ahead and try our first iteration here. So we'll go through each one, and if the ith one has a account number that is equal to the key's account number, then we'll return the index at which we found it. If we have an unsuccessful search, then of course it'll return -1. Right? Okay. Let's go ahead and call this now. So int index is equal to linear search. I called it linear search, didn't I? Yep, linear search. We'll pass in the accounts, n, and the key. I think that was all, right? Yep, the key, except that accounts is already an array, so it is a pointer. Key, is that a pointer though? How do I make it into a pointer? Ampersand. And then I'll say printf found my account at index %d and the line and index. So where should I find it? Based on this right here? Index 0. Right? So GCC. Oops, nope. I wanted previous GCC. There we go. Sorry. We're going to have to put this into the header file. There we go. The prototype into the header file. Uh-oh. Then, sorry. Key, so array sub I, that's a regular old structure, so we use the dot operator. But key is a structure pointer, so we need the arrow there. There we go. Now we can run this. And if everything works out, then we should find it at index 0. Excellent, we found it. Okay. Now, to prove that this is actually working, let's search for a different one. Let's search for Grace Hoppers. Right? And we should find this at index 4, the last one. Hey, okay, so it's working. Let's search for something that does not exist. We would expect a negative value, right? -1, did not find it. Or didn't find it at index, any index, so blah, blah, blah. 1, 2, 3, 4. So let's go ahead and restore that now. That's a pretty good implementation, but what is it good for? It's only good for bank accounts. So what I want to do is I want to make this generic now. I want to take bank accounts away and make this into a generic void pointer so that I could give it an array of integers. I could give it an array of doubles. I could give it an array of anything that you want, right? Of course, I'll need to change that into a void pointer as well. Here's the array that you're searching. Here's the number of elements that you're searching. And here's the key, right, that you're searching for. Okay. Now, if I try to compile this, of course, it's not going to be able to work with this because what's account number? Account number is something that is tied to a bank account. Key is not a bank account. It is a void star. So I could follow the same pattern as my comparator, and I could, force them to be. I could cast the key and array as bank accounts, but then I'm back to square one. Right? I want this to be generic. I want this to be for any types. Okay, so I can't just do that. Key, whatever. So ideas. What I need to do is I need to bring in that third component there, the comparator. And to do that, I need to, where is it? Find const void. There we go. I need to pass this in as a parameter. There. That's not the syntax there, but it'll be star CMP. Oh, there we go. There we go. And there. All right. Now, the syntax that we just learned is, what is this? It is a function pointer. Oops. It is a function pointer that returns an integer and takes two const void star pointers. All right. Let's go ahead and fix this in the header file before I forget. There we go. And I think we still won't be able to compile here because there are too few arguments that we've provided to it, and also I've got these question marks still in there, right? So, how do I make this comparison? I now have a comparator coming into this thing, right? So I need to compare those two elements. If the comparator says that they are equal, in other words, it returns 0, then I know that I've found what I'm looking for. 1, 2, 3, 4, 8, 7, 6, 5, 4. Oh, that's not it. 3, 2, 1. That's not it. 1, 2, 3, 4. Oh, 0. Those are equal. There you go. All I need to do is pass in the ith value and the key. Right? So array sub I and key. Right? Just like I was doing before. But instead of going equals equals bank account, or account number, or last name, or whatever you're doing, I'm handing that logic over to the comparator. Now this is still not going to compile. Oops, or at least it'll give me warnings, hopefully. Yep. Too few arguments over there, but also here. Invalid use of a void expression. Okay. So it takes const void star and const void star. The key is a const void star, so I don't need to do anything to it. But what about array sub I? Is that a memory address? It's the ith element. And if these are structures, then dereferencing it using the square brackets, that means it's a regular old structure. So how do I take that regular old structure and turn it into a pointer? Ampersand. Still not enough yet, though. All right? Let's find out why. I'm actually interested to see what it'll do. Here we let's fix this over here so that goes away. Oh, I never made an account number comparator. So let's do that really quick. By number. There we go. I need this. So here's another comparator. And what would I do? I would steal this. And then, of course, I actually could call my integer comparator from before if I hadn't deleted it. But I'll just go ahead and do it this way. If x is less than y, these are bank accounts now. Account number is less than y's account number. Then I'll return -1. Else if steal this, greater than. They're out of order, so I will return something positive, else return 0. Okay. And then I can pass this into my new version of linear search here. That was the order, right? Okay. If not, we'll find out here in a moment. All right, there we go. So it's going to actually run. It'll run, but I don't know if it'll give me what I'm looking for. Oh, found my account number at 0. I got lucky. Let's go ahead and try another one here. We should expect this at 4. Nope, we didn't find what it was looking for. Okay, so it is definitely broken. We just got lucky here because it cropped out at the first one. So what is this warning about right here? Dereferencing void star pointer, right? So remember what a void star pointer is. It's a generic pointer that's pointing to an address in memory. Is that address in memory 4 bytes? Or is it 8 bytes? Or is it 50 bytes? We don't know. So how can you possibly dereference it when you do something like this? How do you know where the ith one is? If you've got 5, like I do here, 5 bank accounts, the first one, of course, that's easy. That starts at this memory location because that's where the array starts. But how do I know where the second one is? How do I know that it's 4 bytes away or 8 bytes away or 50 bytes away? I need to tell the function. Right? So what else do I need here? I need the exact same things that Quicksort had. There is the array. There's the number of elements in the array, and the comparator, of course. I've got those 3 things already in common. What am I missing? What's the 4th element here? It's the size of the elements in bytes of each element in the array. So that if you've got first element and second element, you know that it's, well, if I start here, then it's 4 bytes away, or it's 8 bytes away, right? Because it's big, or it's 50 bytes away because it's even bigger. So I need that if I'm going to do any generic programming. So let's go ahead and add that over here. There's the size. That's the size in bytes of each thing. Before I forget, let's go ahead and change it over here so that it's size of. Now I'm searching bank accounts, right? So how many bytes does a bank account take? Size of bank account. Account. There we go. Okay. And this will still compile. Of course, I still have, oh, too many arguments? Oh, okay. I needed to change also this over here. There. Now it should compile at least, but of course it still won't work, right? We're going to get lucky here, right? There's me getting lucky again, and here is me getting unlucky, revealing that there's still a bug in this program, right? All right? So the key is fine. The key is just one thing. It's a const void star, and the comparator expects a const void star. I don't need to do anything with it at all. The thing is, where is the ith element over here, right? So let's go ahead and start to figure this out. Array is the memory address of the start of the array, right? Array sub I is the ith element in the array if the compiler knew how, or knew how many bytes each one took, right? Using this syntax right here, that's just the compiler being smart. Oh, it's an integer array, so I know that the ith one is I times 4 bytes away from the beginning, right? That the first one is at 0, then 4 bytes over is the second one, then 8 bytes over, then 12 bytes, then et cetera, et cetera. Oh no, it's a double array now, so that the first one is at 0, then the next one is 8 bytes away, then 16 bytes away, then 24 bytes away, etc. Right? The compiler doesn't know that here, right? Since it is a void star pointer, the compiler doesn't know what they are, and so does not know how many bytes each one takes. But We do. How do we know? The calling function told us. All right? So, where is each element? The first element is at array. Remember, array is the array that we're passed in, which is a memory address. Now, when you're using known types, array sub I, that's just arithmetic. It's saying start at array and go 0 bytes away. That's it. That's why we have 0 indexing to begin with. That's why it all works out with 0 indexing. It's because compiler it makes the math easier for the compiler. All right? The second element is size bytes away from ARR. In other words, ARR plus size. Right? The third element is size times 2 bytes away. Right? In other words, ARR plus 2 times size. Dot dot dot. The ith element is size times what? Say what? I bytes away. In other words, ARR plus I times size. And this is pointer arithmetic. It's arithmetic because I'm simply just multiplying 2 times the number of bytes plus a memory address gives me a different memory address further away. Right? All I'm doing is computing a memory. Here's a memory address. Add 1 to it. You go 1 byte away. Subtract 1 from it. You go 1 byte previous. Right? That's why array of -1, it'll actually compile with warnings, but that's okay. It'll just go, I mean, here's your array. This is where it begins, and it goes down. You want to go up? Okay, fine, but that's not the array. Go ahead and screw up whatever memory you want, and we'll segfault you out on it. Or it'll be a stack smasher event that we saw when we looked at arrays. So all I need to do is this pointer arithmetic right here. I've already got my for loop giving me the I, right? And there's my memory address. The ith this will be 0 times bytes, so the first element. Then 1 times size, or number of bytes, giving me the second element. Then 2, then 3, then 4, etc., all the way up to the last one. Right? Now, this warning should go away, because pointer arithmetic, okay, you're doing your own pointer arithmetic. I don't have to, the compiler is saying, I don't have to do any guesswork anymore because I don't know what these things are. I don't know that they're bank accounts. I don't know that they're integers, etc. But now, I find my index 4. Remember, I didn't change it, right? I'm looking for Grace Hopper's bank account, which is at index 4. Let's search for something else just to make sure I'm not lying and getting lucky again here. Hey, I found it at 2, right? Etc. What if I find something that does not exist? Oops. There. Now, I've solved this problem for forever. Linear search, all I need to do is give it an array. And by the way, why did I make the array const? Over here with Quicksort, it was not const. Why? Because Quicksort was going to rearrange things for you. It was going to sort them. Searching, I'm not going to change it. So there you go. The number of elements in the array, the size of the array, the key that you're searching for, and finally the comparator to use to say these two things are equal. Here you go. Right? Now you can do any generic programming yourself. But why? This is already written for you. Right? Man, LFind. There you go. LFind, LSearch. What do you think the L stands for? Linear. By the way, what's its signature? It put the key first. Oh well. It does not return an integer. It does not return an index. Instead, it returns the pointer at which it finds it. So here are your 5 elements. That's not it. That's not it. Oh, there. That's what I'm searching for. Here's the pointer to that memory location. Right. And then, oops, that's not what I want. What else? It takes the array that you're searching for, the number of elements in that array, the number of bytes for each element in that array, and finally the comparator to use to compare things. LSearch is the same, except it has a little bit different guarantee. Both of these are in the search library, by the way. What's the difference? One of them simply finds it and returns What do you think it can return if it doesn't find what it's looking for? Come on. I'm going to pull this all the way up so I can actually read it. Come on. All right. So, what could it return? With our version, we return -1, right? Because we didn't find what we were looking for. That's an invalid index. But since this one is returning a pointer, what does it return in the event of an unsuccessful search? Null, right? The difference between these two is it performs a linear search of the key in the array base, which has n member elements and each of size bytes each. The comparison function referenced by compar is used to have two blah 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 in the order, which returns 0 if the key blah blah blah, same thing. If LSearch does not find any matching element, then the key object is inserted at the end of the table. Right? So LSearch, nope, not it. I didn't find it, so I'll go ahead and take your thing and put it at the end. Dangerous if you don't have enough memory to do that, right? But that's its behavior. LFind does not do that. It returns a pointer to the matching member of the array or null if no match is found. So, two different behaviors. LSearch will search and insert it if you don't. Why didn't they call it LSearch and insert? LSearch or insert is what they should have called it. That gets to be a mouthful, so they just called it LSearch. And by the way, you have to read the documentation to find this out. Otherwise, LFind, I think that these names are actually reversed, in my opinion. LFind tries to find it, and if it doesn't find it, it does not insert it. It simply returns null. Right? Well, that's all good for linear searching. Could we do the same thing for binary searching? What would it look like? Well, we could write it, and it'll look exactly like the binary search that we wrote before, except that it'll use, there's binary search, except that instead of a const int star, it'd take a const void star, it would take a const void star key, it would take a comparator, and it would also have to take the number of bytes in each, right? But otherwise, we wouldn't use this syntax. We would have to do our own pointer arithmetic, right? But it would look very much like that. Why that's not in the search library, I don't know. It's in the standard library. But it takes a key, which it's not going to make changes to. They put their keys at the front. I put mine at the end. Because, well, I guess they're correct. Because you're always searching for a needle in a haystack. I was searching a haystack for a needle, which sounds backwards. So, sorry. I do like this one a little bit better. But anyway, we've got our key first, and then we've got our array. We've got the number of elements in the array. We've got the number of bytes each element takes, and finally a comparator. And what does it return? It returns a pointer upon a successful search. It returns null. You have to read the documentation. Yeah, null if no such element is found. Right? But of course, what's the gotcha on B search? It has to be sorted. And it has to be sorted with the same ordering, right? If you sort something in ascending order and then use a comparator that expects it to be in descending order, that comparator is not going to work. Why? Because it looks at the middle and then it starts going off in the wrong direction, right? If it's in ascending order, then it's searching for something smaller, then it should go this direction, but it doesn't. It ends up going that direction. Right? So, if you're going to use B search, it has to be sorted. Not only that, but it has to be sorted in the exact same ordering, using the exact same comparator that you use to sort it. If you don't, you'll get completely different results, as you will witness in tomorrow's lab. We do MLB teams, and we have you sort it in 4 different ways and perform a binary search in 4 different ways, giving you 4 different results for each and every single, on the same exact inputs, because it ends up using a different comparator each time. Right? Okay. Any questions so far? No? This is generic programming, and it's extremely powerful because you can implement these algorithms generically that can be applied to any type. It's so powerful that they just pack the standard libraries already with these things. Qsort, bsearch, you're good to go. I don't know of any language out there that doesn't have these already. The one exception I would say in my head is PHP. Unfortunately, they do not have binary search, but that's because they don't need it. They don't even have arrays in PHP. They have what are called associative arrays, which are basically just maps, and so there's no need to search them because you can just look something up immediately. Right. We won't get into that here, though. Right. All right. Any questions? Otherwise, unfortunately, I've been ignoring online. Sorry. Will you ever do an audiobook, voiceover, A Hitchhiker's Guide to the Galaxy? No, I will not. That would be copyright infringements all over the place. I don't think I have that great of a voice anyway. At least I don't have an emoting voice. All right. All right. I don't know what that means. But anyway. What we'll do on Wednesday is we'll do a little bit of a wrap-up with some miscellaneous stuff like gotchas. For example, it was asked last time, what about the difference trick, where you can take the difference between two things? And you can do that in limited circumstances, but it fails because it is prone to overflow and underflow. What happens when you've got doubles and you don't care about close doubles, right? Those are the same things. What happens when another issue is sorting stability. Should you keep the original relative ordering of things? And I'll show you that it actually does matter for looking at data and stuff. But otherwise, we'll go ahead and save all that for next time. All right. And good luck with your lab. And I guess your hack is due tonight too.